which is a greater perspective that they're designed for high reliability department, in which they're meant to be operated up to 210 degrees Celsius. Obviously, when things go up to high temperatures, they start to break down. So our approach began with last semester, in which we designed mainly the schematic and worked on our understanding of how we were going to go about the test approach, as well as designing the circuit for each test. This semester we focused on actual implementation, designing our PCB, getting it made, and then actually testing it in the lab. So as far as what the actual PCB can do, we managed to test all DC parameters, including input bias current, offset voltage, as well as things such as common mode rejection ratio, at both room temperature up to high settings. And the goal of the board is to allow something in which a high temperature test wouldn't be able to be done with normal equipment. So what we can do is we allow a board that allows quick optimization to whatever test you want to go to. For instance, going from input offset voltage to bias current takes simply removing a resistor, and then you're ready to go immediately. Now, you wouldn't be able to do this in normal room conditions, you'd be able to do this by just taking it off. However, when you're testing at 200 degrees Celsius, it becomes a little bit more of an issue, which is where our board comes in. For this, you can have the board in the oven while testing these parameters, and then so you can have the board in the oven while all the components are rated for high temperature, which allows you to test at both low temperatures or high temperatures, which really gives a perspective of whether the amplifier is going to work for your application or not. So overall, we were able to design a successful board that can be used at any temperature range. We've tested mostly DC parameters, although some AC parameters are possible. We just didn't have the equipment to test noise. We have the circuit on the board to do so. We just couldn't test it ourselves. So anything from DC parameters to AC parameters can be tested for any of the amplifiers that TI makes. With a normal example, we would be just using normal amplifiers, which were the 5 we were assigned. However, you could use any amplifier in any application eventually by just changing the circuit. And if there's any questions or else, I'd be free to answer them, or we can demonstrate out of the model.
So what was the biggest challenge that you ran into with this board?
So there were two big issues. One appeared when we use a servo loop to do most of our parameters. Most things are going to be operating at extremely low voltages. For instance, like most input offsets are going to be microvolts or millivolts, microvolts. So we have a loop servo being at 1001. On one of the boards in particular, we lost one of the servo amplifiers, and it was just causing the board to ping out at 10 volts, whatever we were testing at the time. So it took a long time to identify that issue because it seemed like it was a board issue, but at the same time, it actually was just the potentially you could burn out, which on our initial approach, we took a single amplifier, which is all we used in this slot, which is the OP211, and that amplifier was not always designed to work with the other amplifiers.
What differences did you find in the ICs from, say, -55 to 200?
So whenever you go from a temperature range, like room temperature, everything usually works pretty stably. Like if you test a value, any value whatsoever, you'll usually come up with the same result across most of the amplifiers. However, when you start raising things in temperature, in general, things become more varied. So for instance, if you test it going up to 100 C from room temperature, you might find that it raises like 10 millivolts or down 10 millivolts on the offset current or offset voltage. But when you go up to 210, once again, it becomes more varied. Certain ones, such as gain, follow very linear trend lines. However, some of the others were more varied in how they would the actual range of the value.
Did you document that?
We have all our test results on the actual lobby outside. So we tracked across each temperature range. So like each test, we documented what it was at that temperature range, moved the temperature range up, same test, same circuit, and so on. So each temperature range has a full documentation set of data.
And all your ICs
Well,
passed, I guess?
so what we were comparing to, sorry, I understand what you're getting at now. The TI documentation has a specific range value for what they're supposed to do, and that's what we're trying to match it to. This is meant for people that are purchasing amplifiers to be used, and they want to make sure that those amplifiers are used for their applications.
I've never seen 210 degrees on the spec sheet.
I mean, these are meant for not normal applications. These are meant for like aerospace, the department we're working for is specifically the high reliability department. So I mean, the big one where I think I saw most of the heat happening was when it was right next to a lot of like oil killing equipment. I mean, those things get hot.
You don't have to go too far down, it's not gonna be hot.
Yeah, yeah.
And he didn't mention that one of the outcomes is to produce all the documentation that goes with the CFP. So the outcome is not the CFP, but the procedures